So the impulse momentum theorem, remember, came from Newton's second law, and it relates the change in momentum to the cause of the change in momentum. So on the left side over here, these are two different ways to define impulse. And on the right over here, these are two different ways to define the change in momentum. And it's important to remember that impulse doesn't equal momentum, it equals the change in momentum. So if you have an impulse, there will be a change in momentum. If there is no change in momentum, then there is no impulse. So when we're working with this equation, it's important to realize that this force is the net force. It's often usually there aren't a lot of forces involved. But if there are, it's important to realize that that is the net force, because that came from Newton's second law, so that is the net force acting there. And this is just a different statement of change in momentum, because you get your change in momentum is P2 minus P1. Then you could just have, if mass is constant, then you just need the delta V. So this one over here is really good if the mass is constant. If mass isn't constant, then you'll probably have to do change in momentum and do mv2 minus mv1. But in most cases, your mass is constant. So let's take a look at a problem. All right, so we have a 1,400 kilogram car moving westward with a velocity of 15 meters per second, collides with a utility pole. So I've got a utility pole and I've got a vehicle here. So it's moving initially at 15 meters per second to the west. So we're defining a coordinate system where it's moving to the west there. And it's actually being brought to rest in 0.3 seconds. So our change in time here is 0.30 seconds. And it's going to have a velocity of 0 here. So we want to find the magnitude of the force exerted on the car during the collision. So what do? Well, because this is an impulse momentum theorem problem, I know right now that we're going to use the impulse momentum theorem. But how would I know that? How would I know this isn't an energy or a dynamics question? Actually, we could solve this problem with forces and kinematics. There are different ways to solve this. And actually, the impulse momentum theorem is a nice shortcut to having to do kinematics to find acceleration. I could use kinematics to find the acceleration, and then I could use Newton's second law to find the force. So I could do that. But this actually skips the step of having to go through and find the acceleration. So I know to use the impulse momentum theorem if it talks about changing speeds in time and forces. So if you're talking about forces, speeds, and time, or forces, momentum, and time, anything's with it. Very rarely will they specifically say impulse unless they just want the impulse, and that's really rare. Most of the time you're going to use this impulse momentum theorem to find kind of other variables. So how would I solve this problem? Oh, just write out the impulse momentum theorem. Well, I've got all these different options. Well, I know I'm looking for force, I have time, I have mass, and I have velocity. So I'm going to use the combination that says my net force times my change in time is equal to mass times my change in velocity. So realize this center section is the part that is on the formula sheet. But net force times delta time is equal to m times delta v would work. I use that one very, very frequently. So I'm looking for force. So my net force is going to be m delta v over delta t. Now realize that this equation is for the car only. This is going to be the mass of the car, this is the change in velocity of the car, and this is the net force on the car. There is other stuff going on with the pole. The pole probably doesn't change velocities unless it is enough to cause it to fall over. And that's because there are other forces acting on the pole, like there's all the cement in the ground and stuff, kind of gravity and things holding it in place. So this is just the net force that is acting on the car through the pole. So basically what happens during this collision is the car collides, and there are lots of forces acting on the car. The car has gravity, the car has normal force, but those are equal to each other. But the force of the pole on the car is my net force. So although this is my net force, really this net force is going to be the force of the pole on the car. So this question could have asked, hey, find the magnitude of the force of the pole acting on the car during the collision, and that would be the net force in this case. In other cases, there might be multiple forces that are acting, so you do have to be careful. So you can plug in numbers at this point. So our net force is going to equal mass times our change in velocity. So that change in velocity is going to be V2 minus V1. So you can kind of do that and then sub in that 0 for that final velocity. So for V2, I'm going to sub in 0. So I get that my net force is equal to negative mv1 over delta t. So that is what my net force is going to equal. My mass is 1,400 kilograms. My velocity is 15 meters per second. Ooh, running out of room. And my time is 0.30 seconds. So if we plug this in, you get 1,400 times 15 divided by 0.3. So I get that my net force is going to be negative 70,000. And that'll be newtons. Well, negative what? Well, negative 70,000, my V1 was towards the west. This is negative 70,000 newtons west. Well, that net force would really be 70,000 newtons to the east. So because I have that change with the negative here, that's what this is saying. Now the problem is actually asking for the magnitude. So that's why I didn't include the direction here in my problem, because I was just looking for the magnitude. But if it had asked you for direction, either of these would be acceptable. So if you had written negative 70,000 newtons west or set positive 70,000 newtons east, either of those would have been acceptable answers. But in this case, it's just asking for the magnitude. So you just needed the 70,000 newtons. So that is an example of how to use the impulse momentum theorem. Now, what happens if instead of this car coming to rest, what if it had bounced back? What if it had hit the pole and then bounced for whatever reason? Well, let's take a look at that problem. So is the change of momentum larger if you stop or if you bounce back? Well, let's take a look. So in this case, we're still going to have our net force times our change in time. It's still going to equal our mass times our change in velocity. And that is still going to be mass times V2 minus V1. So if I was looking for my net force, I would still divide by time, m times V2 minus V1 over my change in time. So this hasn't changed much. The only thing I'm going to have is that my final velocity, my V2 here, is not 0, it's 5 meters per second. So if I plug into this equation, my net force is equal to my mass. Well, my mass is still 1,400 kilograms, that hasn't changed. Now, my ending velocity is 5 meters per second in speed, but what's the direction? Well, it bounced backwards. So that means instead of going west, it's going east. Well, I don't want to write west and east in this equation. So what I'm going to essentially do is I'm going to define, in this case, I'm going to define west as positive because that was my original direction. And well, we can define west as negative, and we're going to define east as positive. So basically, we're setting up a coordinate system here. We have north, south, east, and west, where west is going to be negative and east is going to be positive. So what I can do is I can then use those positive and negative signs in here. So my V2, my 5 meters per second is backwards. So that is in the eastward direction. So that is going to be a positive 5 meters per second. And then minus, well, my V1 here was in the westward direction, which I'm defining as negative. So that's going to be a negative 15 meters per second. And then that's going to be all over my time of 0.30 seconds. So what ends up happening here is I have a negative, which becomes a positive. So originally, when the car just stopped, it had a change in velocity of 15 meters per second. It went from 15 meters per second to 0. Well, this car goes from 15 meters per second to 5 meters per second, but actually my change in velocity here is equal to 20 meters per second. So changing directions has a bigger change in velocity and therefore a bigger change in momentum. So when I go through and I plug in, I'm going to get a larger number because I'm going to have that 1400 times 20 divided by 0.3. And that's going to give me 93,333 newtons. Whereas originally I had that 70,000 newtons. Now this net force here is positive. So this net force is still directed to the east, just like my net force was originally directed to the east, but my force had to have been bigger in order to cause the car to bounce backwards in the same amount of time. Now, if it had taken a different amount of time, we'd get a different answer. So this is under the assumption that we did keep time the same, we kept the mass the same, we kept the initial velocity the same. All we did was change the final conditions. So really, really important takeaway here is that whenever you bounce backwards, that change in direction during a collision causes a larger change in momentum than just slowing down or stopping. All right, so one last example. We have a car traveling to the west. It skids to a stop from an initial speed, and we want to figure out how long it takes the car to come to rest given a coefficient of friction. So one thing I really like about this problem is it forces us to pull in information from past units. This is a standard stopping distance problem. We've seen these in both in forces, we've seen them in work, we've seen them in kinematics. This is one more way to solve the problem. I really like this method of solving the problem when it involves time. Kind of like I like the work energy theorem when it involves distance, but because this involves time, forces due to friction, and changes in speeds, I really like the impulse momentum theorem. So looking at this, we have a car that is traveling west, starting off at 20 meters per second. We know the mass of the car, and it is going to skid so that some point later in time it is at rest. This is kind of like the problem with the car hitting the pole, except for this time it is friction that is causing the stop. We have a coefficient of friction which is 0.50. Because it's skidding, that's a sliding friction, so we can't assume that is a kinetic friction force and that it is constant. And then we are looking for essentially the time it takes for it to come to stop. So if I'm looking at an equation to start off with, I'm going to start off with that my net force times my change in time. And because I'm given velocities, I'm going to use the m delta v version again. Like I said, it's my go-to. And then this is talking about a net force, but it only tells me about friction. And I don't even know what my friction force is. I know what my coefficient is. That's where we're going to have to kind of remember how we did this from past units. So if I look at the forces acting on the car, I'm going to have gravity, and I'm going to have normal force. And in the y direction, those are going to be equal to each other. So I can write in the y direction a net force equation that says Fn minus Fg is equal to 0. In the x direction, since my car is moving to the left and friction always acts in the opposite direction, my friction force has to be backwards to the left. So in the x direction, I'm going to have essentially a negative Fk. And that would actually equal my m times a. If I was going to do a forces perspective, I could solve for my acceleration. Then I could use kinematics with an acceleration of my velocities to find time if I wanted to. Now, by making that a negative friction, I am defining left to be positive and right to be negative. And the reason I do that is because I like to keep the direction of motion to be positive. You don't have to, and it just makes sense for friction to be in the opposite direction. Now, because my forces in the y direction cancel, that means that my Fx is my net force. So when I go to plug in up here some of my more relevant variables for an F net, I'm going to plug in negative Fk. And the negative is taking care of the direction, times delta t. And then delta V is going to be V2 minus V1. And I know that since I'm going to rest, V2 is going to be 0. Now I'm making and defining my V1 to be positive. So I've already taken care of the sign for both friction and velocities, for both my force, for both my vector quantities. So with friction, that friction force is going to equal mu k times Fn, by definition, times delta t. And that's going to equal negative mv1. So you can see here that my negatives will cancel out on either side. So if you had forgotten the negative here, in this case, all that would have happened is that you ended up with negative time. You'd be like, oh, time can't be negative, that should have been positive. But if my final velocity hadn't been 0, so for example, I was just slowing down to say 10 meters per second, if I were to leave off a negative, I would actually get an incorrect answer. So you have to be very careful and very conscious of sign when you're working with your vector quantities, especially in this unit. Sign errors are one of the most common mistakes in momentum. And then I know from this equation here that my normal force is equal to my gravitational force, and my gravitational force is equal to mg, so I can replace that with mu k mg delta t is equal to m times v1. And then I also notice that my mass actually cancels out. This is a really cool result. This tells us that no matter the mass of this car, it's going to take the same amount of time for it to come to rest. So they didn't even have to tell us what the mass of the car was for us to solve this problem. And then solving for delta t is then going to be v1 over mu k times g. So really, in order to find the time, I just needed to know my initial speed, I needed to know my friction, I needed to know g. Now, they like to ask lots of conceptual questions, so what do I know from this? I know that mass doesn't matter. I know that if I were to double the initial speed, it would take twice as long to stop. If I were to say take this to the moon, where gravity was 1/6 that of Earth, it would take 6 times the time for it to stop. And if, let's say, I had double the coefficient of friction, then it would take half the time to stop. So the bigger the coefficient of friction, the quicker you can stop, which just kind of makes sense. So plugging in numbers, our time is going to be our initial velocity, which is 20 meters per second, over our coefficient, which is 0.50, times 9.8, 9.8 meters per second squared. So if we were to have 20 divided by 0.5, 9.8, we would get a time of approximately 4.1 meters per second to two significant figures. Not meters per second, seconds. About 4.1 seconds. So if it had been 40 meters per second, it would have taken us about 8.2 seconds. So that's how you can use the impulse momentum theorem. There are really cool and amazing things I could do with this problem to make it even more complicated. For example, right here, my friction was just equal to mu k times my normal force. But if, for example, I was on a ramp, and let's say my car was going up the ramp, and I wanted to figure out where it stops on the ramp, then my normal force wouldn't equal gravity, and I'd have to do more net force equations. So always think about how these questions can relate to past units, because they love to throw momentum and energy and forces and everything all together in one big free response question. So I hope that gives you a better idea of how to solve problems. Have a good day.